IFT at the Autónoma in Madrid, and then he moved to Oxford for his first PhD. First postdoc. Then he obtained a Rutherford Fellowship, which he took to Cardiff, and then he went back to Oxford as a faculty, and he has been there now for a few years now, right?
I think in total it's been 8.5 now. 8.5 years.
Yeah, so he's gonna tell us about his work on data structure and photometric redshifts. Please, David.
Okay, thank you very much. Yes, I'm going to talk about cosmology from. Can you hear me all right? Yeah. Okay. Cosmology from photometric surveys. I think there's a big overlap between the people here and the people that were present in November when I gave a similar talk. So I'm going to try to not bore you too much. I'm going to try to focus on something else that I didn't focus too much on during that talk. So hopefully it won't be too boring. But yeah, so it's a slightly more technical thing, but it's sufficiently easy to understand that I am hopeful that if there's non-cosmologists in the room, it will still be interesting. Yeah, so before I start, I want to thank Raúl for inviting me. It's the first time I was in Donostia. It's been really lovely. It's only a couple of days, but I really loved it. And I'd also like to thank, oops, what's happening now? Interesting. Okay, let me stop sharing then. There you go. Am I still sharing screen? I think I'm not sharing screen. Let me go. Next screen. I'll just share the whole thing. It's okay. Okay. Yeah. So thanks to Raúl, but also to Mateo and everyone else who took me out last night. It was really nice. If I don't make any sense at some point, it's their fault. It's not. Okay, so does that work? No. Oh man. Okay, all right. Yeah. So let me first start by motivating the kind of science that we want to do with these types of data sets. Before I get into these technical details, so a lot of the cosmology that we know nowadays comes from observations of the cosmic microwave background, and essentially the easiest thing to think about the cosmic microwave background is giving us a picture of what the density of the universe looked like very, very early on at redshift of 1,000. So we see these small fluctuations around the mean, which tells us that the universe is pretty much homogeneous with really small overdensities and underdensities early on. These overdensities and underdensities are going to grow over time due to gravitational collapse. They're going to form the large-scale structure that we see around us today, and we have these beautiful pictures from surveys like this is 2MASS, where you can see these very nice filamentary structures that form and voids and all this rich cosmic web. And arguably, one of the successes of modern cosmology has been to connect these two regimes. So you can take a density field that looks like like what the CMB tells you it looks like. You can put it in a computer and then just let it evolve forward just using gravity. You guys are expert on this, and you get these very nice kind of filamentary structures and things like that in many simulations that then you can compare with actual measurements, and you know, at least qualitatively speaking, it looks really, really nice. Yeah, and so we can try to extract information from these late time overdensities in different ways. So let's think about what we do. So the typical quantity that we're going to be talking about is the matter over density. So it's just the amount of extra density at a given point in space with respect to the mean. Let me see if I can remove this stuff. Yeah. So this is the typical quantity we're going to be looking at. And there's two ways of extracting information from this. One is to look at the evolution of this quantity as a function of time. We know that it's going to grow because of gravitational collapse. But the way in which it grows as a function of time depends on the background cosmology and the background expansion. So you can try to infer cosmological parameters from that, from just taking snapshots of these density fluctuations as a function of time. And we'll show an example of that later. So that's the time evolution of this, but you can also look at the distribution of these overdensities on different scales. And can I actually check how many of you are non-cosmologists in the room? Okay, so then then it's okay if I take some time for this. Great. So the way we usually look at the scale dependence, or the how these overdensities distribute on different scales is by looking at this kind of complicated quantity called the power spectrum, which is actually not that complicated. Mathematically, the only thing you're doing is you're taking your three-dimensional measurement of the overdensity field, you transform that to Fourier space. So you look at uncorrelated Fourier components. And you do that because statistically, it's a nice thing to do, essentially, because all these modes are statistically independent. You square that, and you average over all equivalent modes, essentially. So what it tells you is basically the amplitude of density fluctuations, or the amplitude square of those fluctuations as a function of scale, where large scales are on the left and small scales are on the right. So the scale dependence is also going to depend on cosmological parameters, arguably more mildly than the growth potentially, although for example, the positions of these wiggles in the power spectrum that we call the BAO, the baryon acoustic oscillations, they depend more or less sensibly on the cosmological parameters. So we can extract information from these, but first we need to actually make measurements of the density field itself. And how do we do that? Well, so for what I'm going to be talking about is about one specific way of going about it, using photometric surveys. So a photometric survey is a survey of galaxies where you don't measure spectra, you measure the photometry of galaxies. That means instead of measuring the full spectrum of the galaxy, you integrate it on a few order 5 different bands. So you basically get a very, very coarse-grained spectrum for each galaxy. That means that you don't really know what the redshift is or what the radial position of the galaxies are. So the best you can do is kind of divide your sample up into different shells of galaxies that are probably close together in the radial positions, and do the analysis in a two-dimensional way. So we're going to be looking at projected overdensities, but I'll talk more about that in a second. You probably are familiar with the current ongoing photometric surveys. These 3 guys here, KITS, HSC, and DES, from which we've been able to learn interesting things about the late-time universe, and I'll talk about some of that in a second. In the future, these kinds of constraints are going to come from many surveys, but one of them, the one that I'm most excited about is the legacy survey of space and time, LSST, at the Rubin Observatory. So this is one of the latest pictures of LSST. It's pretty much completed in terms of building, so we're quite excited and scared. In terms of cosmology, well, so it's going to cover a huge part of the sky. In terms of cosmology, the Dark Energy Science Collaboration is going to try to do cosmology with these 5 different probes. The 2 I'm going to highlight here are weak lensing and galaxy clustering, which are the ones that with which you actually do large-scale structure, i.e., you probe these density inhomogeneities. So what are these 2? So galaxy clustering, the idea in galaxy clustering is you try to use the overdensity of galaxies as a proxy for the overdensity of matter in the universe. And there's good reasons to believe that the relationship between both overdensities is just linear on sufficiently large scales, and this proportionality constant here is what we call the galaxy bias. So basically, that means that if we look at galaxies on large scales, it tells us roughly what the density fluctuations are on those large scales up to an unknown amplitude parameter, essentially. But in reality, the relationship between both things is actually quite complicated. It's some kind of non-local, non-linear, and stochastic relationship between the 2. You guys have worked a lot on that here. The interesting thing about galaxy clustering is that it's a local tracer of these matter fluctuations, meaning that if you look at the distribution of galaxies that lie at a given redshift, you're probing the large-scale structure at exactly the same redshift. And that's not going to happen for weak lensing. So this is the good thing that you can do with galaxy clustering. Because of this issue with galaxy bias, that means that you can't really measure the amplitude of density fluctuations with galaxy clustering on its own, at least on large scales. And so it's hard to get competitive measurement of growth just using galaxies. because you don't know what the evolution of it is over time. Because they are local, that means that the scale dependence of these overdensities is not diluted as we will see for weak lensing. So that means that you can still get some information about the scale dependence of the matter fluctuations, at least on large scales with galaxy clustering. And on small scales, these linear bias breaks down, and it's developing a model for this is quite hard. So it's questionable to what extent you can actually go deep into the small scale regime. Although, as many of you know, there's been advances in this in the last few years, some of that led by you guys. All right, so now let's think about weak lensing. The idea in weak lensing is you look at the observed shapes of galaxies in the background. So the photons coming from these galaxies, they're going to see their trajectories perturbed by the intervening matter because of the gravitational potential of this large-scale structure along the line of sight. So that's going to perturb the original shape of the galaxy when you observe it. And then you can look at the correlations in the shapes of these galaxies as a function of for example, the distance between pairs of galaxies. And that will give you, then you can turn into an estimate of what is the amount of structure that these photons have traveled through. So you can build maps of the corresponding density field. When I talk about weak lensing from galaxies, this is also usually called cosmic shear. So shear meaning just the deformation in the shape of the galaxy. And that's usually labeled with a gamma letter. So if you see gamma in the following slides, it just means weak lensing. The nice thing about weak lensing is that this perturbation in the trajectories of photons, this gravitational lensing effect, is caused by all of the matter in the universe. It doesn't distinguish between luminous or non-luminous matter. So that means that this is an unbiased tracer of the matter distribution. We don't have this bias problem. That means that then the complementarity of galaxy clustering and weak lensing is quite good because it allows you to actually solve for complementary things, right? So weak lensing doesn't have a bias problem, so you can measure growth more easily with it potentially than with galaxy clustering. Because weak lensing is a projected tracer, essentially when you look at the perturbations in the shapes of galaxies that lie at a given redshift, you're not looking at the matter fluctuations at that redshift, but at all of the intervening ones from that redshift to you. So that means that you're integrating, you're basically averaging out scales on a very long radial kernel. So that washes off a lot of these features in the power spectrum. So you can't really do that with weak lensing. And because you don't have the bias problem on small scales, it's arguably better to or easier to go to small scales and have a nice theoretical model for the matter fluctuations than it is for galaxies. So this complementarity is what makes the combination of these two approaches very strong. This combination is usually called the 3 times 2 point analysis because you look at the correlations, 3 different correlations between galaxies and weak lensing, galaxies with galaxies, galaxies with weak lensing, or weak lensing with weak lensing. But this is kind of the flagship analysis for these kinds of surveys, LSSP, etc. Okay, so as we said, we're looking at projected tracers. So you're not looking at the 3-dimensional distribution of galaxies, which would be this, what I've called this big delta G, but the projected version of this on the sky, right? So you take all the galaxies that probably lie at similar redshifts, and you make a 2-dimensional map on the sphere of the distribution of those galaxies. And here, for example, you have the distribution in redshift of a bunch of samples of galaxies. This is from one particular experiment. This is from HSC. So then what you see is a projected version of that where you've integrated along the line of sight, weighting it by the redshift distribution of these objects. But still, it's true that if you've chosen galaxies that more or less lie, for example, at this redshift, even though there's some spread, then the corresponding map is going to be a map of the large-scale structure at these types of redshifts. So the tracer is still local as long as your redshift distribution is more or less well peaked. And just to reinforce what I said before about weak lensing, that's not the case for weak lensing, right? In weak lensing, the corresponding radial kernel that translates between the 3-dimensional matter distribution and the shear field is this weak lensing kernel, which is itself a cumulative integral over the redshift distribution. So it's some kind of integral of the redshift distribution itself. So if you're looking at, for example, the weak lensing effect from galaxies, this would be a ridiculous redshift 7, right? But just for the for illustration purposes. The kernel actually has almost no support at those redshifts. It actually peaks at lower redshifts and then goes down again. So you're actually integrating over all of these structures along the line of sight. And the same for other galaxies that live at other redshifts. And this will be important when we start discussing the effects of uncertainties in the redshift distribution. One final tracer that I haven't talked about. So we've talked about galaxy clustering and weak lensing. We can also do weak lensing of the cosmic microwave background. So these first photons that were emitted in the early universe, they're going to see their trajectories perturbed by the intervening large-scale structure, and that's gonna redistribute the anisotropies in the CMB. And these non-trivial correlations between anisotropies that lensing creates can be used to reconstruct the integrated matter structure along the line of sight in a similar way as you would do for galaxy shapes. And so the best way of thinking about CMB lensing is just thinking of another lensing of galaxies, but these galaxies now lie at a super high redshift, at a redshift of 1,000. So it's something that is basically going to have correlations with anything that lives between redshift 0 and redshift of 1,000. So that in that sense is great because it correlates with absolutely everything in the universe. And we'll see more on that in a bit. I should say, please interrupt me at any point if you have questions. I don't know how it usually works, but I'm happy to take questions whenever. Yeah, okay, so I'm going to be talking a lot about power spectra, and people tend to find this confusing because now we're talking about two-dimensional quantities projected on the sphere. These power spectra now don't live in Fourier space, but in harmonic space. So what you do is you take the spherical harmonic coefficients, and if you don't like those, just keep thinking about Fourier coefficients. And then you look at correlations, so products of two of those. And so the corresponding power spectrum is what we call the angular power spectrum. The origin of CL, Matteo has a very nice theory about, so he can tell you about that in the future. But this angular power spectrum is basically related to the three-dimensional power spectrum between the two corresponding quantities, the three-dimensional matter density and galaxies, for example. And the relation is, again, another integral along the line of sight, a projection along the line of sight with the product of the two radial kernels of the two things that you're correlating. So this is just some example of for example, the cross correlation between galaxies and shear in, I think this is in Kids and Dichtels galaxies. And again, the way to interpret this is when you see one of these plots, you have angular scales on the x-axis and then the amplitude of perturbations on those scales in the y-axis, the amplitude squared, where large scales are here and small scales are down here. Actually, no, it's DES, it's not Kids. Yeah. So, so just to motivate the kind of science that we can do with this, before I get into the more practical issues of doing this kind of science, I just wanted to highlight this work that was led by one of our postdocs at Oxford, Carlos. I went into more detail, I think, in my previous talk, so I won't really touch on it for too long, but I just want to motivate, get you excited that you can actually do cool stuff with these photometric surveys. So you may have heard about this S8 tension. The idea is with weak lensing and galaxy clustering surveys, the two main cosmological parameters that you can measure are omega m, which is the abundance of matter in the universe. So how much of the total energy of the universe is made up by normal matter, but non-relativistic matter. And then the other parameter is this kind of abstract parameter called sigma 8, which is a measurement of how large fluctuations are. So it basically tells you how clumpy the universe is. So these yellow, red, and blue contours here are the constraints on these parameters by three different experiments, large-scale structure experiments compared with the measurement from the CMB in gray here. If you look at one particular combination, which is basically the combination of parameters that lies in the perpendicular direction to this kind of elongated contours, so that's what people call S8, which is this combination of sigma 8 and the square root of omega m. You can actually see that all these measurements from large-scale structure are consistently lower than the measurement that you get from Planck. So in Planck, exactly what you do is actually you measure the clumpiness of stuff at really high redshifts. You infer cosmological parameters, and then you extrapolate at low redshifts and say, okay, then things should be this clumpy at low redshifts. But it turns out that what we measure directly at low redshifts is significantly lower than that. So why is that? Is that because things are evolving at a different pace than you would expect from lambda CDM, for example? Is the growth different? And so that's what Carlos wanted to answer in this paper. And in order to do that, you can do this idea of tomography, right? So imagine that you measure the angular power spectrum of weak lensing. That's going to be proportional to sigma 8 squared, so to the amplitude of matter fluctuations. But you can't really tell which redshift this amplitude is mostly coming from, because you don't have redshift, as we said, for weak lensing, you have this very broad kernel. But then if you look at the cross correlation with galaxies and then the autocorrelation with galaxies, you can then narrow down which redshifts you actually want to measure this one. So, for example, the cross correlation will be proportional to sigma 8 squared times the galaxy bias at the redshift of the galaxies. So that way you can tomograph the growth. And then in order to measure what the galaxy bias is, then you can look at the autocorrelation and break the degeneracy that way. So it's this idea of tomography. So we can build a history of growth. So this is Carlos here. Okay. So what he did here is basically putting together all the projected data sets that we had at that point together into a single coherent data analysis pipeline and do this kind of measurement. I won't go into the details of how that's done. But again, the motivation was trying to figure out what the history of growth is in the last few billion years. So I think, yeah, so that's the result. So what you're seeing here is in the x-axis is redshift, so past and present. And the y-axis is this S8 of Z. So just, again, think of how clumpy the universe is becoming as a function of time. The blue line is the prediction from Planck if you extrapolate assuming lambda CDM, and then the red measurement is the direct measurement that Carlos made. Of course, the specifics of this function depend on how you decide to interpolate between different measurements and things like that. But the salient point is that at this redshift, so between redshift 0.2 and 0.6, you have the amplitude of fluctuations is definitely lower than you would expect with lambda C. And I say definitely, I'll go into what the significance is of this later. But you can tell basically at which redshift this is happening. This doesn't say that things are definitely compatible with lambda CDM at earlier redshifts, because the reason we have these small error bars here is because we have most of the data on these redshifts actually, right? So here we have larger error bars. It could actually go down as well. So this is not saying that the evolution is markedly different from lambda CDM. And in reality, if you try to fit this data with lambda CDM, you will get a good fit to the data. It's just with a lower amplitude than you would predict from Planck. But it's nice that we can pinpoint that all of these surveys are giving you this consistently different lower growth at these redshifts. So the different contours here, and there's all of many other combinations in the paper, they correspond to different combinations of the data set, and they're all consistent in telling you this. Of course, we can then do that. Yep.
Yeah. So I mean, assuming that only this redshift range 0.25 to 0.5 is the culprit of this tension, I guess you should, and if this is real, I guess you should be able to see that also in direct measurements of of the growth rate at those redshifts from redshift space distortion.
Yeah.
So I was wondering whether the current data is enough to kind of see this effect in growth or not.
Well, so this is a question that the referee asked us for this paper. I don't know if you were the referee of the paper, but it's hard to say because essentially the F sigma measurements are a derivative of this function. So if we try to put those measurements in the same kind of units as this, is the error bars are sufficiently large that we can't really tell anything from those measurements. What we would like to do is actually to combine both. If you had a nice way of basically parameterizing this curve as some kind of free function, a Gaussian process or something like that, you could use those as a prior on the derivatives of that Gaussian process, and these as direct measurements of the function itself. So that would allow us to potentially say whether you can actually get a good fit if you include both data sets in a coherent manner, for example. That might be nice. But at least with current data, we couldn't. It was difficult to actually interpret the redshift space distortion of data in this context. Thanks. Yeah, so we try to, I mean, this is assuming that we don't know anything about growth. If you assume that you know what growth is, then you can just put constraints on S8 without any redshift dependence and put it in the context of all the other measurements. And it, you know, it's because we've combined so many data sets together, it's really tiny error bars, which is nice. So we get a very, very, I think this is the tightest constraints on this thing, if you believe those constraints, and the tension with Planck is at the level of 3.5 sigma. So that's the significance of this difference, right? Right, so this was basically to get you excited about the kind of science that we can do, but you need to be extremely careful about propagating all kinds of uncertainties and systematics in the data. So I'm going to talk about one particular source of systematics, and there's many of them. But I just picked this one obviously because I worked on it, but also it's one that I think is relatively easy to understand and fun to think about, which is issues with the redshift distribution of your galaxies. Okay, so as we said, the way redshift distribution come in is when you try to make a theoretical prediction for the CL, you need to project the three-dimensional power spectrum along the line of sight with the two kernels of the two things that you're correlating. So in the case of galaxies, it's going to be just the redshift distribution itself. In the case of weak lensing, it's going to be some kind of integral of the redshift distribution. So how does that affect things? So if before we go into technical details, let's just try to build some intuition of how this works. So I've taken a fictitious redshift bin here. This would be the P of Z, the redshift distribution. Let's say that it's peaked at redshift 0.5 or 0.6, something like that. This would be the redshift distribution, and this is the corresponding lensing kernel, which basically picks up after redshift 0.5 or something like that. That's what you get. Then you get the galaxy power spectrum here and the weak lensing power spectrum. So you can see in the weak lensing power spectrum, this is what I was saying. All these wiggles have disappeared because you've basically integrated them out by projecting so many scales together. Now, what happens if you don't know exactly what your redshift distribution is? So imagine that actually all the redshifts that you use were biased low, and so this is actually the real redshift distribution. First, what is the consequence of that on the lensing kernel? So that's going to lower the amplitude of the lensing kernel as well as making it a bit narrower. Which then means that the effect on the weak lensing power spectrum is almost exactly just scaling it down by a constant factor everywhere. The effect on the galaxy power spectrum is twofold. It affects the amplitude of the galaxy power spectrum, but that's going to be degenerate with the bias. The other effect is it shifts these features, these BAO features, and the reason is that the physical size of the BAO is going to have a different angular scale if it's at this redshift or if it's at this other redshift because of projection effect. So that's why the wiggles get shifted around. But the dangerous thing is that it's very easy to actually try to fit this new power spectrum by just changing the cosmological parameters a little bit. I did this by eye, so you can probably find even better parameters. But if you shift omega m by like 0.05 and sigma I by another 0.05, you could probably get a good fit to both of them. So if you don't know well what your redshift distribution is, you're going to bias your cosmological parameters. Or in other words, there's a strong degeneracy between uncertainties in the redshift distribution and the cosmological parameters. Okay. So just a bit more intuition. What's the other thing that you could do to a redshift distribution? You could shift it around. The other obvious thing to do with a Gaussian is to just make it wider, for example. So if you make it wider, because the probability distribution needs to integrate to 1, that means that you need to lower the amplitude of the POC. That doesn't really affect the weak lensing kernel almost at all. It changes it a little bit, but not much, because again, the Q of C, so the weak lensing kernel is an integral of this, and the area below this curve is going to be the same always. So it doesn't really change the weak lensing power spectrum, the weak lensing kernel too much, which then means that the weak lensing power spectrum almost doesn't change if you change the width of your redshift distribution. The amplitude of the galaxy power spectrum actually changes by a lot, and it's again because you're lowering the amplitude of this lensing kernel. Sorry, of this redshift distribution, and it comes as the square of it when calculating the galaxy power spectrum. So again, you can fit this by just changing the bias a little bit, and so you'll get a wrong inference if you don't correct for this kind of width effects. Okay, so with this in mind, how do we actually put constraints, or how do we actually measure these redshift distributions? In the ideal case, which would be great, you will have a large sample of spectra for the same sample of galaxies for which you're trying to do this kind of analysis. And so in that case, you can just histogram those redshifts basically and make a histogram. You get a measurement of the n of z, and you're done. And this is an example from this paper by Martin White with using LRGs from the DESI legacy survey, for which they actually have lots of spectra. But this is almost never going to be the case, right? Because you're going to try to go as deep as possible in redshift, for example, or you're going to because you want to have as many galaxies as possible when you're doing weak lensing, for example. So this is almost never the case. And if you go deep enough, taking too many spectra is very expensive, and the samples for which you can measure spectra are usually not the same samples for which you want to do weak lensing, for example. So they're going to be small and non-representative, meaning that they're not the same types of galaxies for which you're doing the analysis. So one thing that you can do is you can reweight maybe the samples for which you have spectra to make it more similar. So you reweight in color space to make it similar to the one to your own sample. But that's not always possible because if you don't have any spectra at a given position in color space, then you can't weight nothing by something and get something. And also, especially when you go to very high redshifts, the spectra that you get, they have their own systematics, and especially at high redshift, it's going to be tough to get good redshifts. So one particular solution for this is this idea of clustering redshifts or cross-correlation redshifts, which you may have heard about. And the idea is very similar to what I was telling you about before in terms of tomography, right? So the idea is, imagine that you have this is the redshift distribution of your photometric galaxies, and you slice it up into narrow windows of redshift with some spectroscopic sample that you have on the same patch of the sky. The amplitude of the cross correlation between your photometric galaxies and each of these slices of the spectroscopic galaxies is going to be proportional to the amplitude of the redshift distribution. So if you look at that cross correlation, so what I'm plotting here is as a function of redshift here, which means for each of these spectroscopic samples, you have the in the z-axis you have the cross correlation with the photometric sample as a function of scale. But if you just look at the amplitude, it basically follows the redshift distribution. The nice thing about this is that the spectroscopic galaxies just need to lie on the same part of the sky. They don't need to follow the same color distribution, for example, as your galaxies. So that's an advantage. The first problem, however, is that what you get, so this cross correlation is actually not directly proportional to the P of Z, to the redshift distribution, but to the product of the bias of your photometric sample with its own redshift distribution. So if what you care about is the redshift distribution, then you're going to need a model for the bias. Second problem is that at high redshifts, you may even not have any spectroscopic redshifts, or the ones that you have, it might be quasars, which quasars are great, but you may not have enough of them to actually make an accurate measurement of the redshift distribution without huge error bars. So how can we solve, in particular, this second problem? So I'm going to talk about two potential solutions. One of them is using CMB lensing. As I said at the beginning, CMB lensing basically correlates with absolutely everything. So if you have issues at high redshifts, try CMB lensing and see what happens. And so I want to illustrate that by looking at kind of an extreme example of this, right? So we want galaxies for which we have almost no information about the redshift of these galaxies, and which live actually at very high redshift. So you want a sample that lives super far away where you can't really get redshifts. So that's kind of the worst case scenario. And that's what happens for radio continuum surveys. So I'm going to do a small aside talking about radio continuum surveys for a bit, but it will be useful later on. So just bear with me and we'll get back to redshift distributions in a bit. All right. So radio spectra are extremely boring. Radio spectra are basically power loss dominated by synchrotron and free emission from those galaxies. There's very few features. The one that is quite important is this 21 centimeter line from neutral hydrogen, but it's a very faint line. So can you use it? So you can use it if you spend a lot of time just targeting specific galaxies and trying to resolve this spectral feature, and that's what an H1 survey is. So that's good because you get spectra, but you can't really do it for many galaxies because you really need to integrate the light coming from that galaxy for a very long time. So usually they're not too deep. So you won't get redshifts for very far away galaxies this way. The other option is to do intensity mapping. So in this case, what you do is you say, okay, I'm going to forget about individual galaxies. I'm just going to point my telescope at a given region in the sky. I'm going to integrate all the light that comes from everything in that region. And that means that I will basically add up the 21 centimeter line from all the galaxies that lie in that region. So let's say you take like half a square degree or something like that, and you just get all the millions of galaxies that lie in that region. So it's going to enhance this feature, and you may be able to detect it, but that's at the expense of having low angular resolution. But most importantly, as we will see later, the issue of foregrounds. So that's if you forget about angular resolution and instead focus on redshifts. The other thing you can do is forget about redshifts. So ignore the 21 centimeter line altogether and just say, I give up on that. I just measure the continuum spectrum and I'm done with it. Because it's a continuum spectrum, it's a power law. I'm not going to get redshifts. So I might as well just integrate over the whole spectrum, which enhances the signal to noise of your galaxies, and you can actually detect radio galaxies really, really far away in redshift. That's what a continuum survey is. It's basically a survey without any redshifts, but which goes to very high redshifts. So one example of this is this LOFAR 2-meter sky survey. It's called LOTS. It's a continuum survey at roughly 150 megahertz. So you have a measurement of the density field from that projected density field up here. And I'm going to talk about the cross correlation of that with single lens. So I'm going to talk about the analysis of this first data release, which was a small patch of the sky just for 100 square degrees. But it was, it was interesting. So what's the idea here? So just to give you an idea of how uncertain the redshift distributions of these samples are, these are 3 potentially perfectly valid redshift distributions for this LOTS sample. The one in red is direct measurements of redshifts, but these are photometric redshifts from pan stars for many of these galaxies. The one in green is spectroscopic redshifts for a very, very small subset, which are not even lying on the same part of the sky. This is a different radio survey. The sample might be different. But we have spectra for them, and it's not so many of them. We have only 500 galaxies with spectra in this case, and that's the green one. And then the blue one is essentially a model. It comes from a simulation, but just think of it as a model based on measurements of the luminosity function for galaxies, which you need to extrapolate using the halo model or whatever to really high redshift. So there's strong theoretical uncertainties on these. And what you can see is that the main difference between all this is the high redshift tail. So how far in redshift they go. So you can with a single kind of fitting function, you can fit all of them if you just change how far in redshift you go. This redshift tail. And just for comparison, you can see here the weak lensing kernel that the CMB lensing kernel. So what we wanted to figure out is whether we can actually distinguish all of these redshift distribution by looking at the cross correlation. And so let's look at some of these plots again. Well, so this is the measurement of the power spectra. So you have the galaxy autocorrelation here, and the cross correlation with CMB lensing. So the cross correlation is a nice kind of almost 5 sigma detection. So you can see that most of these points are not 0, which is good. So let's see what we can do about that. I just realized sometimes I'm calling the redshift distribution P of Z, and sometimes it's N of Z, but they're exactly the same thing. Okay, so again, let's try to build some intuition. Actually, well, before that, if we look at the type of the shape of these power spectra, they are extremely boring, right? They're again kind of power loss, so there's no feature that we can actually detect because it's all being washed out. So the main thing we can learn from this is something about the relative amplitude of these 2 power spectra. So what affects that amplitude is it's 2 things: is the galaxy bias and the width of the redshift distribution. So if we change the galaxy bias, that's going to change the amplitude of the autocorrelation with the square of that bias. It's going to change the cross correlation with just 1 power of that, but it's basically going to affect that amplitude for both. If we change the width of the redshift distribution, however, we saw that affects the autocorrelation quite strongly. But the cross correlation is almost not changed at all. And the reason for that is that this cross correlation essentially is proportional to the integral of the N of Z, and the integral of the N of Z is always 1 by definition. So that doesn't really change much. So there's 2 conclusions from this, actually, because you can break the degeneracy between these 2. You could constrain the tail of the redshift distribution by looking at CMB lensing. Anything that controls the width of the redshift distribution, you can constrain this way. if you turn that around, instead, what you can say is that because this cross correlation with SIMB lensing is so insensitive to uncertainties in the width of the redshift distribution, then you can always use this cross correlation without having to worry too much about the uncertainties in your redshift distribution. So that's also good. But we were more interested in actually trying to constrain this tail.
This also depends on sigma 8, right?
Yeah.
But
So,
I guess you do.
so in this case, we're saying we gave up on trying to measure sigma 8 from this and say, okay, let's believe sigma 8. There may be a tension, but it's not at the level that we can resolve with this. So could we use this cross correlation, for example, to say something about astrophysics, right? If we can tell what the tail of the redshift distribution is, that we can say something about which modes of the luminosity function or something for radio galaxies, which are better.
Here you're assuming a tail, but in some cases you have confusion between different lines, so you have really interlopers.
There's no lines here, so this is a continuum survey. What you can have here is a different mixture of star-forming galaxies and AGNs, which might affect your redshift distribution more than just by strengthening the tail or not, right? It might be give you like a doubly peaked redshift distribution or something like that, which we're not parameterizing here. But yeah. Is this what you were asking? Yeah. So we haven't worried about that, and I'll show you that now we need to worry about this with the new data. But yeah, that's a good question. Okay, so from this data, you can actually hopefully I convince you that you can say something about the width of redshift distribution. And this is actually something that I did with Emilio Bellini. Maybe you know this guy. He's a very nice guy. So these are the constraints that you can get with this really poor detection of the cross correlation. So you can definitely tell that most probably this VLA measurement is the most reliable one, and that there's something about the extrapolation of the luminosity functions that doesn't really work. You need to assume something about the evolution of the bias, and that's important. But for this measurement, we saw that as long as you didn't assume something super crazy about the evolution of bias, the result was kind of solid. So it didn't, this qualitative result that this is the kind of tail that you get is solid. So definitely there's something wrong with the photosys from pan stars that suppresses this tail. Good, all right. Now, so what we've learned here is that cross correlations of something with SIMB lensing can tell you you can use that to constrain the width of a radial kernel. So then you can turn that around if you think, oh, sorry, yeah, before I get into that, sorry, let me go back. So these are measurements from the new data release, which is a much larger area. And now we have a much higher detection of the cross correlation with SIMB lensing, and the types of constraints that we can get on the redshift distribution are also much tighter, and we can actually distinguish between these two modes of star-forming galaxies versus AGNs, for example. And so this is being led by Szymon Nakonecznik from Warsaw. He was visiting me 2 weeks ago, which was the first visit we could get after the pandemic, and he taught me how to say his name. So much higher signal noise, and actually we can see that potentially we could even break the degeneracy with sigma 8 and potentially make a measurement of sigma 8, but we'll see. Right, so what I was saying is you can use cross correlations with CMB lensing to measure the width of your radial kernel. But if we go back to what happened for weak lensing, remember that in weak lensing, what determines the width of the radial kernel is not the width of the redshift distribution, but the mean of the redshift distribution. Right? So if now instead what you look at is the cross correlation between CMB lensing, which I've called kappa here, and normal galaxy lensing, you can potentially say something about the mean of the redshift distribution instead of its width. And this is something that Naomi here demonstrated using KITS and KITS data and Planck and ACT. So this is a super low kind of signal to noise measurement, because this is all of these measurements of this cross correlation so far are low signal to noise. Low meaning there's definitely a detection, but it's not like a 10 sigma detection. So, but she could show that she could actually measure the shift in the redshift distribution to be some number that is positive, definitely. So this is for the highest redshift being in KITS. So she could say there's definitely a shift, and you need to correct for it. In the future, when this signal to noise grows, and it should grow significantly, you might be able to do something more precise than just that. So that's interesting. How long have I been going on?
Like 40 minutes.
Okay. All right. I'm going to try to talk about one other thing, and then I'll stop. Yeah. Okay, so this is how we can use symbilancing for this. So again, just to recap, we were trying to solve the problem of how to characterize redshift distributions for stuff that lies at very high redshift. The other thing that we have a very high redshifts is the 21 centimeter, the intensity mapping that I was mentioning before. So 21 centimeter intensity mapping goes to very high redshifts, and it has good redshift resolution because you can trace the large scale structure on small scales in the radial scales. So could we use that to do clustering redshifts, as I mentioned, instead of using spectroscopic galaxies? And so the idea is that at face value, if you just assume that you have a perfect 21 centimeter experiment, the answer is yes. So if you have, so here what you have is the uncertainty on the mean of a given redshift bin, using clustering redshifts with 21 centimeter for a given experiment. Let's use, for now, we're going to focus on this experiment called Hyrax, which is quite promising. These are the constraints that you could get on that, compared with the requirement for something like LSST. So how well you actually need to measure this parameter in order not to degrade your cosmological constraint from LSST by a large amount. And you can definitely meet that requirement if you use 21 centimeter in an ideal way. The issue with that is, as I mentioned, for intensity mapping, we have the problem of foregrounds. And the idea is the following: if you point your telescope at the sky and you just integrate all the light that's coming from that region of the sky, you're gonna be integrating not just the 21 centimeter line, but also all the other continuum emission. Okay. So if you look at the spectrum that you measure for one of these patches of the sky, it will have many contributions. You'll have a wiggly contribution, this black line here, which is the 21 centimeter line. So these are just the large scale structure at the redshift corresponding to the 21 centimeter line at this frequency. So that's wiggly. And then all the other components are just the continuum emission, synchrotron emission, or free from either from our own galaxy or from other galaxies in the same patch. Well, you can see that there's like 4 orders of magnitude difference. So you're trying to disentangle this 10 to the minus 4 wiggles on top of this spectrum. Right? But the good thing is that this is wiggly and this is not. So you can separate your measurement into small scale fluctuations and large scale fluctuations. And the large scale fluctuations are going to be dominated by foregrounds. The small scale one are going to be the 21 centimeter. However, that has one unfortunate consequence, which is that when you're looking at things that are smooth in frequency, that means that these are things that are dominated by long wavelength modes in the radial direction. So if we look at this kind of abstract picture, so what I have here in the y-axis is scales in the radial direction. So these are Fourier scales. So small scales are here, large scales are here. And then the same thing for transverse scales, so angular scales in the x-axis. So foregrounds are going to dominate some region here on the low K parallel region. And if you do realistic simulations of foregrounds, something like that, it's usually at the level of 10 to the minus 2 in inverse megaparsecs. Okay, so you can forget about measuring any fluctuations on those scales. But now what we said we want to do is we want to determine the redshift distribution of photometric surveys. And photometric surveys are almost exactly the opposite of a 21 centimeter experiment. A photometric survey essentially loses all the information on small scales in the radial direction. And if you do the math, the typical uncertainty in your redshifts is pretty much corresponds to a co-moving scale, which is the scale at which foregrounds start dominating. So there's almost no overlap between the scales that are covered by a photometric survey and the scales that are covered by intensity mapping experiment. So that means if you try to look at the autocorrelation of galaxies in a photometric survey and H1, so this is 21 centimeter, because of statistical homogeneity, the 2 wavelengths need to be the same in order for you to measure something. But there's no region in the K parallel, K perpendicular space where you can make the 2 measurements. So if you want to be conservative, you should assume that this power spectrum, cross power spectrum, is going to be 0. Depending on how well you can actually do foreground removal, maybe actually you can measure this power spectrum. But if we're realistic or at least conservative, we should assume that it's not possible to measure. So that means that this whole idea that we could maybe do clustering redshifts is probably difficult. So what we did with Caroline, who I think some of you have met, is trying to look at the higher order correlator. So you can look at the bispectrum. So that means the 3-point function in Fourier space. So now you have one galaxy density field and two measurements of the H1 on 2 different scales. Now, if we look at this from a mathematical point of view, I'm going to try to convince you that there should be a non-zero correlation between 2 small scales, small radial scales in the H1 and 1 large wavelength mode in the galaxies, which is what you need, because these only live on large scales, these only live on small scales. So mathematically, because of statistical homogeneity, and this will sound like Greek to, well, not Greek, but I guess a different language, Chinese, to those of you who are not cosmologists, the sum of these 3 Fourier modes need to be equal to 0. So that means that these Fourier modes need to lie on a triangle, essentially. And it is possible to build a triangle with 1 very short side and then 2 very long sides. And that's what we call the squeeze limit of the bispectrum. So you have a squeeze triangle. So that's mathematically. I think more physically, I think it is intuitive to realize that the small scale clustering should correlate with the large scale over densities. So if you think of your universe, of a universe where you have a long wavelength fluctuation, so think of it as something that is being traced by the photometric galaxies. Effectively, that means that in this region, the density of stuff that you have is lower than in this other region. So if you have lower density, you should also have lower clustering. So things should be less clumpy here than they are here. So the local variance, meaning the square of the density field here, should be higher than it is here, which means that the local power spectrum of H1 should correlate with the local value of the large scale density field. So that means that this 3-point function should be non-zero. So what Caroline did here is trying to develop an estimator for this and then quantify how well you could actually constrain properties of the redshift distribution for example, LSST by using this. So, okay, let me try to explain this and I'll probably finish after this. So you have here, it's the same as before, you have as a function of redshift, the uncertainty that you could get on the mean of the redshift distribution. Confusingly, I've decided to plot that here in co-moving scale rather than in redshift, but just think of it as, again, just a delta Z, so how much you've shifted the redshift distribution. These black lines are 2 different sets of requirements for LSST. So this is how well you actually need to measure it. And then you have the bright or the kind of light contours. These are the kind of errors that you could get using the power spectrum rather than the bispectrum. And so these areas covers the constraints that you could get if you assume that you have really, really good photocies. So with really, really good photocies with an uncertainty of 0.02, you could probably do it. But with more realistic ones, like the ones that we will actually get from LSST, which will be this end, is completely impossible to measure this. And in fact, your chances of being able to do this redshift calibration depend very, very strongly on how good your photoses are. Then the darker band is what you will get with the bispectrum, and you can see that there's some dependence on how good your photoses are, but the dependence is much milder. And in any case, you can always calibrate the redshift distribution using this to the requirement that you get from LSST. So this is quite promising. It's also a technique that you could use for other things, right? You could look at this squeeze limit. So basically having 2 small scales in the H1 and 1 large scale in the photoses to measure primordial non-Gaussianity, which also kind of peaks for the local type of primordial non-Gaussianity. It peaks on these same configurations. So you could use the same technique for that. You can do clustering redshift also with the Lyman alpha forest, which has a similar problem to 21 centimeter by using this type of method. And you could use it for other fancy things that I'm not going to go into the details of. Yeah, so I have like 20 other slides that I'm not going to go through. So I'm just going to end here, blast through all of these. And thank you.
Thank you, David. Questions?
I have one. So thank you very much for the talk. So one question that I was wondering is, you have shown how the projective spectra actually washes out all of the information about the BAO. But I was wondering, so I can understand this very well in, like in the line of sight direction because you are integrating all that, right? But in principle, it doesn't have to be completely washed out on the angular direction, does it? In the sense of like, if you think about like thinner slices instead of like super deep slices, you could still see like some BAO, right?
Yeah, definitely. So, exactly. So the idea, if I go to the very beginning, so these wiggles here, these wiggles are here because that's the angular size of the BAO at this redshift, right? But if your redshift distribution is much broader, if it goes from here to here, then you're mixing up fluctuations where the wiggles are on these scales and fluctuations where the wiggles are on these scales and on these other scales. So if this is very broad, you're going to mix them all up and you're going to get some kind of smooth power spectrum like this, which is what you get from lensing. So yeah, as long as you can actually get good enough photosys, you will be able to measure these BAOs, but only for clustering. I don't think there's any way you can do that with lensing.
So related to that, how's the state of these things? So how's the thinnest slice that you can have in photosys? And can you observe it, or is a perspective for?
No, there's measurements of the BAO with DES, for example, with Red Magic, right? Red Magic has really good photometric redshift, so you can do this with that for sure. It's never going to be as powerful as spectroscopic redshifts, but you can do it.
Yeah, actually, that was like my next question. Like, I mean, in few words, what would you think is the advantages of photosys measurements with respect to the spectroscopic measurements? You have mentioned a couple already.
Yeah. So in terms of galaxy clustering, the main advantage of photometric surveys is that they give you much higher number densities. So if you want like a high signal to noise or a high low noise kind of measurement of some projected over densities, then it's great. And so which means that this type of science, this is a personal opinion, okay? I'm not going to base it on numbers, but I think it's correct. Trying to measure the BAO is a fun thing to do, but it's never going to be as competitive as spectroscopic surveys. What photometric clustering is very powerful at is doing the tomography, basically. So you can take almost any projected quantity for which you have no redshift information and then just slice it up into redshifts and look at the evolution of different things. And so here we focused on sigma 8, but you can think of, so with another student, we also did this for just probing the background evolution of gas pressure in the universe as a function of redshift. So anything like that, I think that's what you want to use projected clustering for, and FNL as well. So FNL is something that is on sufficiently large scale that you don't really care about having really good photosys, so you could in principle do. And also FNL it is quite critical for FNL to have a high density tracer. So that's why, in my opinion, something like LSST will be quite powerful for that.
Thank you. So we're talking about photometric and spectroscopy. What about the middle ground, narrowband surveys? What's your personal opinion on that?
No, I mean, I think I was talking to Ramon about that, Raúl about that. Yeah, it's a perfect combination, right? It's almost like the optimal cosmological survey would be to do something like that. So you guys work on JPAS, just make it as large as possible, I think. That's Spherex, I think, is the other version of this, which will be quite powerful for all of this.
Let me ask you the obvious question. So if you focus on the tension between lambda CDM and Planck lambda CDM and your tomographic measurements, like at redshift 0.5 or so. So what is the systematic error on the redshift distributions that would solve this tension, and whether you could rule out that such potentially big redshift distribution by doing the clustering redshifts with eBOS galaxies, for instance?
That's a very good question, actually. Yeah. It's a very good question, but I think to some extent it's been addressed by the DS people, right? But where do I have this? So all of these, right? Actually, yes. So all of these power spectrum measurements, blah blah, from DS, the redshift distributions, for example, for DS, they are calibrated with a given spectroscopic sample, which is actually not spectroscopic, is this Cosmos sample, right? And you can show that because this Cosmos sample has its own systematics, particularly at high redshifts, you're going to get slightly biased redshift distributions. And the way in which these are biased is usually by shifting them down. And so that that essentially bias your measurement of S8 if you don't know that. So that's where and it's something that always happens at high redshift. So I think that's where clustering redshifts or any of these other things I think is quite powerful to do. And in the future we're going to get this problem the whole time. So it's something that we need to do.
But in the plot of growth versus redshift, the biggest or the most significant tension was not at the high redshift, right? It was at redshift 0.5.
Yeah, but if
it
you
was not in the middle.
Yeah.
So you think that there is no room for we could not have gotten the redshift distribution so wrong at those redshifts.
Okay, so I don't have the plots here, but if you this is roughly, just think of DES, for example, as something that where you have measurements on roughly this same redshift, right? So you have galaxies that live at up to, let's say, redshift 1.5 or something like that. You might think that you're measuring the growth of fluctuations at this redshift, but in reality, because this is what happens with the weak lensing kernel, you might have galaxies here, but the weak lensing kernel actually peaks at much lower redshifts, right? And so what you see is that this is actually, even though you have galaxies at redshift 1 kind of up to 1.5, but most of the galaxies are actually like here. Most of the constraining power from weak lensing actually comes at this redshift, because that's the structure that you're actually probing. But that means that you need to calibrate the redshift distributions of things that live on these higher redshifts. And so the problem is still there for the redshift distribution, basically. Even though most of the constraining power is here, it comes from galaxies that live here. So you need to constrain the redshift distribution of those.
Right. So I'm not sure I understood. So now if you take this red curve, how much you would have needed to shift the redshift distribution so that it agrees with Planck?
You would need to shift it in this direction in order for it to agree with Planck. And I forget the number. There's a paper by Shahab Yutaki that looks at this. And it's, so yeah, I can't give you a number basically, but there's papers that have looked at this. And it's by an amount which is compatible with the difference in the redshift distributions that exists for this same sample from DES. If you measure that redshift distribution with Cosmos, which has photometric redshifts and has kind of a few issues, and you measure it again using a smaller number of galaxies which have spectra, you can see a kind of coherent shift in the redshift distribution. And just that amount is enough to actually make something that is either more compatible with DES or to enhance the compatibility with Planck, or to enhance the compatibility between DES and KITS. So it's by an amount that is, within the realm of possibility, actually.
Thank you.
Related to that, what's the range of scales that you're considering in this study? Because in DS, they discard smaller scales, and when they put back smaller scales, then the clustering and the lensing start to have a distancing flow problem, the cosmology change.
That's a very good point. So we haven't been particularly careful at that. Essentially, what we've seen is the work that all these collaborations have done in the past, DES on the one side, KITS and HSC. Separately, they've always been able, at least in the past, actually the latest DES analysis is a lot more careful than what I'm going to say, but most of these analyses were able to use the lensing autocorrelation up to an L of 1,000 or 2,000. Okay, so we use that kind of scale cut for lensing. Now, one caveat to that is the fact that that was a good enough scale for each of these experiments separately doesn't mean that it's good enough when you combine them together, because you're going to get a much higher signal-to-noise measurement of everything. So maybe if you have systematics with variance, you should be more careful. And we were not, because we were more focused on the kind of growth reconstruction than on actually getting the most reliable constraints on SA. We do get constraints on SA because why not? But that's a pinch of salt. Maybe we should have been more careful about variance, for example, which live on these very small scales. That's the answer.
Thank you. Okay, let's thank David one more. He's going to be here for a few more hours in case you want to chat more.
Yep.